It is time for homework. Woohoo. So we're going to start with 247, which is hydrostatic force. So it is in 2.5, and I'm only going to do part B here. Part A is not as bad. In fact, both of these, this problem's easy. A rectangular dam is 40 feet high and 60 feet wide. 40 feet high and 60 feet wide. All right. Assume the weight density of water is slightly different than what we've been doing in the lecture videos. They probably took this problem from somebody else. And compute the total force on the dam when the surface of the water is halfway down the dam. So this is where the water is. Halfway down, this is only 20 feet. There's a lot of ways you can set this up. And it wants us to find the force on the dam. Well, we are good math students. We have our notes. And our notes say that the hydrostatic force is going to be the integral from A to B of the weight density of our liquid, in this case water, times the width function, times the height function, or depth function, depth, dx. Now there's a lot of ways that you can come up with x. You define it. Is x going to be the distance from the top of the dam? Is x going to be the depth of the water? Is x going to be the distance from the bottom of the dam? X can be any of these things. You choose. See, I'm going to make S be the depth. Again, all of these work. Well, let's have x equals 0 be here. And this will be x equals 20. Because then look what happens if this is our choice of x. And it doesn't matter. You can have x be other things. If this is our choice of x, then what is x doing? So again, this is going to be x equals 0. And this is going to be x equals 20. So to integrate this entire blue water region, it'll just be, well, starting from x goes from 0 to 20 of the weight density of water, which here we're saying is 62.5, times the width function. Well, this is easy. It's a rectangle. It doesn't matter how deep we are. The width is always the same. The width is always 60. Times the depth. Well, I said x is the depth. So we don't have to do anything fancy here. X is just that depth. Right? We're done. Just calculate this integral. I don't want to take the time to do it by hand, even though it's a simple integral. Just use a calculator. Because I don't want this video to be, I really don't want this video to be a full hour long. 62.5 times the integral from 0 to 20 of 60 times x dx. 750,000. Again, you can answer in pounds. It's better to do it in tons, but you don't have to. Why is it? It's mad because of the dx. Divided by 2,000, 375 tons. That's the better answer, but I'll take both. We can check our answer with the textbook, 247b. And there it is, 700. It disappeared, but it was there. I saw it. Right there. Great. Easy. Done. Man, hydrostatic force. I sleep. Centers of mass. That's where the real good stuff is. Do 276. Use a calculator to draw the region, then compute the center of mass. Use symmetry to help locate the center of mass whenever possible. So 276. The region is between y equals square root of x, y equals ln of x equals 1, and x equals 4. Oh, I made a note to talk about what to do when there are two functions, but then I went off of my notes and just improv'd. And when you do that, you miss the important note comment. I'll include something in the assignment description to remind you guys what to do. Okay, so we're going to draw this picture as we're instructed with the calculator. Square root of x, ln of x between x equals 1 and 4. All right, so looking at this lamina in this region, assuming a constant density, what have we got? So again, my guess just off the bat is maybe going to be 2.5, 2.5 comma 2. That's my guess. Oh, 2.5 comma 1. This is my guess for the center of mass. Again, it should be somewhere around here. If we get a center of mass way up here, we got a big problem. Now, the center of mass can be outside the region. It's fine if it's outside the region. And it will sometimes be outside the region, but it just shouldn't be in wacky no man's land. And it certainly can't be anything bigger than the toppest point or smaller than the bottomest point. Don't judge my English today. It's been a long day. So here we go. So we're going to need the mass, which is the area. We're going to need the moment with respect to the x-axis and the moment with respect to the y-axis. So we use our formulas. The mass is just the density times the area. What's the area between these two curves? Top minus bottom. Which one's top again? Top is the square root of x. Square root of x minus ln x dx. Really? We're going to have to use integration by parts maybe, but we're using calculators for this anyway. The moment with respect to the x-axis, if we hypothetically get the x and y-axis formulas confused, hypothetically, we could check our answers. We could use our notes. Moment with respect to the x-axis is rho over 2 times a function squared. And when there's 2, you just take the difference of each function squared. It's going to be rho times the integral from a to b. Sorry, rho over 2 times the top function squared minus the bottom function squared. Yeah, all right. We're not even doing this second one with integration by parts. Maybe there's, you can probably use a u substitution with integration by parts on this guy, but either way, we are using a calculator here. And the last one is just rho x dx, I believe. Oh, and a and b are 1 and 4, by the way. Let's fill those in. We don't know rho. It doesn't matter. Integral from 1 to 4 of x times top minus bottom. So let's calculate each of these. Shall we? So we do the total mass. It's going to be rho times the integral from 1 to 4 of top minus bottom. Total mass is about 2.121 times rho times that density. And let's make this a little easier on ourselves. Let's call this m. The moment with respect to the x-axis, does it like this? Yeah, it likes this. Great. Is that integral rho over 2 times the integral from 1 to 4 of square root of x squared minus natural log of x squared. Making sure I typed it out correctly. So that's about 2.452 times rho. And the moment with respect to the y-axis is just going to be rho times the integral from 1 to 4 of x times the square root of x minus ln of x dx like so. About 5.060. It's entirely possible I've made a mistake. We'll see though. Remember, x bar is that moment with respect to the y-axis. divided by m. Because again, with respect to the y-axis is the x-coordinate stuff. Y bar is moment with respect to the x-axis divided by m. We're going to get that our center of mass is just x bar comma y bar. And we can find those right here. X bar is moment with respect to y divided by m, which is about 2.3. Ooh, hold on. Let's label my guess. I guess 2.5. It's 2.385. Nice guess, Jason. Woo! What's the center of mass with respect to the y coordinate? It's about, oh, pretty close. 1.156. Beautiful. And again, this you could calculate by hand. This would require integration by parts. And this might work with integration by parts. I'm not sure. You can use a calculator for this. And we could graph it. But the graph is going to look so similar to my graph anyway. Let's not bother. Great work, buddy. All right, let's do another problem. Do 285. Let's get rid of all this beautiful stuff. I don't want to let it go to my head. Find the area and the centroid. Use symmetry whenever possible. Ah, this should be easy. Quarter circle, the square root of 1 minus x squared. Wait, why am I doing this problem? And we're specifically looking... I don't think this looks like anything new. Specifically looking for... Let's not do 285. 285 is boring. I don't want to be bored. Let's do 287. X squared and x. All right, and specifically, draw the region enclosed by the curves. All right, so it's going to be, this region. Under pink, above orange. So again, center of mass is, we do have some sort of symmetry. Center of mass should be at about 0.5. Should be 0.5 exactly, I imagine. And then, oh no, it might not be. It should be a little less than 0.5, I think. Maybe 0.45, comma like a third or something like that. Yeah, it's not quite this, but roughly this. Maybe 0.5 would have been better. And then like something a little higher. It doesn't matter. It's somewhere around here. Okay. It's easier to draw it, I think, for me, than it is to put the points. It's somewhere around there. Ah, it just looks bad though. Anyway, let's not label this one. And how do we find the center of mass? It's just like the last one. Okay. So, the total mass just going to be rho times this area. It's x minus x squared from 0 to 1. Dx, the moment with respect to the x-axis. Which one was that? Rho over 2. It'll go from 0 to 1. I have the first guy squared minus the second guy squared. The moment with respect to the y-axis, we just rho, integral from 0 to 1 of x times the first guy minus the second guy. All right, same as the last problem. Why did I want to do this one? Use symmetry wherever possible. But it's not quite symmetric. I mean, it's symmetric. So here, it's symmetric about this line. Oh wait, no, it's not. I thought it was. No, I think it is symmetric. I think it's just our scale. See, these should be squares. Since these are rectangles, that's why it doesn't look quite symmetric. But I think if we actually made these squares, then it would be symmetric about that line. But that's not as useful right now. Okay, I'm really getting. Oh, there's some fun stuff you can do with that, but I'm getting off topic. We can just plug this into a calculator and get the right answer. I'm not going to do it. I don't want to waste your time, but that's how you set it up. 280, 291. I'm hoping this one's more interesting. Find the generalized center of mass. Generalized just meaning we have parameters here. Find the, oh yeah, all right, I'm getting excited already. Find the generalized center of mass between y equals, so this is some downward facing parabola, x equals 0 and y equals 0. And we're skipping that theorem. So just doing that first one. Center of mass between a squared minus x squared. And again, depending on what a is, it'll look different. The idea is it's a parabola, and specifically it's a parabola above. Right? It's always positive because it's a squared. The vertex is always positive. We have symmetry. So no matter what a is, we've got this, and bounded by x equals 0 and y equals 0. What? Hold on. That there's two regions, no? Why does it specify x equals 0? Oh, okay. You're going to do this to me right now, textbook? Okay. So I don't know why it specifies x equals 0. I think it doesn't want the x equals 0. I just want to double check and make sure I'm doing the problem as it was intended. I'm losing. It's trolling me. It doesn't let me click the button. Huh. Hold on, I got this. Everything is going to be fine. I'm checking on another browser. This is 291. Another browser. Okay, so it just wants you to look at the positive stuff. So again, there are two regions. I'm glad I checked. It says, let's only look at the positive one. I don't think it specifies that. Yeah, it doesn't. Okay, so first it wants the center of mass of this region here. So again, you might guess that it's kind of right here. Maybe it's like right here in the middle of this box. It'll be different depending. I can't draw a guess unless I want to use stuff with A's. And that's a little hard. But yeah, I'm guessing that visually it looks kind of like this. Let's calculate it. We're going to calculate it just like we've been doing. So we need the mass. We need the first moment with respect to the x-axis. We need the first moment with respect to the y-axis. The mass is going to be the density times the integral. Actually, does it just say centroid? No, it does want center of mass. Okay. So it's going to be the density integrating from 0 to what? Well, it depends on what A is, right? Depends on what A is. We're looking at this region in the first quadrant. Oh, so we need the x-intercept here. Well, it's y equals a squared minus x squared. The x-intercept is when y equals 0. Oh, okay, that's nice. X is plus or minus a. So we'll just be going up to a. All right. And just this function is a squared minus x squared. This is just the area under the curve from 0 to a. That's the mass. First moment, that's going to be rho over 2, integral from 0 to a of the function squared. Moment with respect to the y-axis is going to be rho, integral from 0 to a of x times the function. Just using those from our formula. Now we got to calculate these out by hand. So let's have a nice, we'll do these nice and color coded. Red, blue, green. We already used red. It's fine. This will give us rho. We can take the antiderivative. A squared we treat as a constant. So this becomes a squared times x minus 1/3 x cubed from 0 to a. Wait, hey, where'd my color go? Keep the rho in front. Can't factor out the a squared because they don't both have it. When x is a, this becomes a cubed minus 1/3 a cubed. And when x is 0, they're both 0. So we have 1a cubed. We're subtracting 1/3 of an a cubed. We only have 2/3 of an a cubed left. So that's the total area of the function. Sorry, the total mass of the function. 2/3 a cubed would be the total area. All right, well, now let's find this first moment. There are two first moments here. We're looking at the first moment. It's going to be rho over 2. We can't take the antiderivative yet. We need a FOIL. This would be a to the 4th minus 2a squared x squared plus x to the 4th. That's rho over 2. Now we can take the antiderivative. 1/5 a to the 5th minus 2/3 a squared x cubed. A is a constant. Plus, oh, what did I do wrong? I made a mistake. Do you see it? We're not taking the antiderivative with respect to a. We're taking the antiderivative with respect to x. So this is just a to the 4th times x. And again, you should be able to double check by taking the derivative of this with respect to x. See if we get that integrand again. All right, so that gives us rho over 2. When x is a, this becomes a to the 5th minus 2/3 a to the 5th plus 1/5 a to the 5th. And when x is 0, it all zeroes out. They're all a to the 5ths. 1 minus 2/3 is 1/3. 1/3 plus 1/5. Third plus 1/5 is 8/15. This becomes 4/15 rho. A to the 5th. Because we have 1/2 of 8/15 is 4/15. That's too much math in my head. We'll see if we mess up. And the last one is just rho. We have to distribute 0 to a of a squared x minus x cubed. Antiderivative is 1/2 a squared x squared minus 1/4 x to the 4th from 0 to a. When it's a, we get 1/2 a to the 4th minus 1/4 a to the 4th. And when it's 0, it's just 0. We get rho times 1/2 minus 1/4 is 1/4. A to the fourth. Gosh. You get 1/4 rho times a to the fourth. So what does that tell us about the center of mass? Tells us that, well, x bar is the center, is the moment, first moment with respect to the y-axis. 1/4 rho a to the fourth divided by the mass, 2/3 rho a cubed. So the rows cancel, and we have 1a left over on the top. What about the numbers? 1/4 divided by 2/3 is 1/4 times 3/2, 3/8. Maybe. Let's check our answer before we even find the other one. The x coordinate of the center of mass, is that 3/8 a? All right, should be up. All right, if we're really being pedantic, a either has to be positive or this will be 3/8 times the absolute value of a. Let's just make a be positive. Does that look like the center of mass? Does it look like that region? Does it look like this region would balance on this line? Yeah, it's believable. All right, and center of mass for the y is going to be blue divided by red. And we're really going to start drawing behind my head soon. We got McDonald's colors here. We got an a squared in the top. 4/15 divided by 2/3 is 4/15 times 3/2. That's 2/5 maybe? Maybe? Is 2/5 a squared look good? Let's check. Does that green dot look like the center of mass? Does it look like it's in the middle? Kind of does, right? Kind of does. What if we got the right answer, everyone? What if it's right? Check our answer. A over 6. Do we have that? No, we don't. 4a squared over 5. Wait. What? Wait, 4a squared over 5 can't be right. The book's got to be wrong, right? There's no way. There's no way. All right, this is my point. This is the book's point. Not a chance, right? Not a chance. I'll think about this after the video, but I'm looking pretty suspicious with their claim that it's the white dot. Please. Anyway, that's it for the video. Let me know if you have questions. Good luck.